Okay, this is chapter 13, the second half of it. We have previously gone through problems involving molarity. Big thing to know is molarity is moles divided by liters. So if you have to find the molarity of something, you have to find how many moles of it you have, figure out how many liters of it you have, divide the top number by the bottom, and you've got your molarity. Molarity is kind of funny. It's one of those conversion factors in the sciences that's written somewhat cryptically. Quite often you have conversion factors that are written as fractions, like density. You know, you'll see things like the density of a solution is 1.8 grams per milliliter. So it's real obvious that's a conversion factor. Molarity, it's not quite so obvious. Molarity, instead of writing it as a fraction, they write it with one symbol. The trick is remembering when you see that symbol, rewrite it for what it is. It's a fraction. It's a conversion factor. So we went through molarity problems, how to use molarity as a conversion factor. Next type of molarity problem to look at then would be dilution problems. Quite often in a lab, you're mixing one solution with more solvent, or you're mixing one solution with another one. Either way, when you do that, the concentrations within that solution change. So when you mix two solutions together, all the concentrations, all the molarities end up changing. You've effectively diluted the solutions. So, anytime you mix two things together and you want to keep track of the molarity or the concentration of the stuff you're interested in, you use the dilution formula. The dilution formula, guys, is a beautiful formula. It's one of the simplest formulas in the sciences. It's only got 4 terms. It's M1V1 equals M2V2. Sometimes you'll see it written like this, MIVI equals MFVF, where essentially M1 is the initial molarity, the molarity of the stuff before it's mixed. V1 is the initial volume, the volume before it's diluted, before it's mixed. M2 is the final, typo there, that should have said V2. V2 is the final volume, the volume after mixing. So you can see why sometimes it's written as molarity initial, volume initial, molarity final, volume final. More often you see it as M1V1, M2V2. So, very easy formula to use. Any kind of dilution problem that you encounter, you'll always know 3 of these terms. So there's only 4 terms in here. You'll know 3 of them. You simply do a little bit of pretty simple algebra, and you solve for the term that you don't know. So a quick example here. Let's say you have some 12 molar hydrochloric acid. Hydrochloric acid is typically sold in the concentrated form as 12 molar. That's the nasty stuff. That stuff's kind of rude. You don't want to spill that on you. It hurts. That stuff burns when it hits your skin. So let's say you take 5 milliliters of that stuff. You mix it with water, and you make sure that the final volume is 100 milliliters. What is the molarity of the hydrochloric acid in the diluted solution? Well, you know you're going to use the fact that it says dilution. Hey, you know you better be using this formula, right? Yeah. What's the initial molarity? Before it's diluted, it's 12 molar. So M1 is 12 molar. How much stuff was diluted? Oh, 5 milliliters of 12 molar. Oh, that's the initial volume. V1 is the initial volume. That's my 5 milliliters. So this is my M1, V1. I'm trying to find M2. I'm trying to find what's the molarity after it's been diluted. The final volume, the volume that it was diluted to, 100 milliliters. All I have to do is solve this equation for M2. When they say solve the equation, what that means is set it up so that the thing you're looking for, the thing you're trying to solve for, is the only variable left all by its lonesome on one side. Well, right now he's not all by its lonesome. M2 is also mixed with 100 mils. How do I get rid of that 100 mil? I divide this side of the equation by 100 milliliters. And if I divide this side of the equation by 100 mils, I have to divide this side by 100 mils. Hey, that part cancels out. That's the whole reason we divided by the 100 mil. So at this point, M2, the final molarity, he's all by his lonesome on one side. We've solved for M2. To get the answer, it would be, of course, 12 times 5 divided by 100. And we would say, oh yeah, after we do that procedure, we take 5 mils of this, we dilute it to 100 milliliters, it's going to be 0.60 molar. So we started out with the real nasty hydrochloric acid, that 12 molar hydrochloric acid. Take 5 milliliters of that nasty stuff, dilute it to 100 mils. Oh, now it's 0.6 molar. Not anything I'd want to soak in, but really 0.6 molar hydrochloric, you could spill it on your hands, just wash it off real quick, you'll be fine. This stuff, you spill it on your hands, you better wash it off really quick, and even then, trust me, it's going to burn. It's going to hurt. That is some concentrated hydrochloric acid. So again, that's the dilution formula. Just to maybe give you a better appreciation for that formula, again, it's typically written as M1V1 equals M2V2. Sometimes you'll see MIVI equals MFVF. You'll sometimes see it written as this. C1V1 equals, the initial concentration, the initial volume, has to equal the final concentration times the final volume. You don't have to use it with molarity. You can use it with other units of concentration. Check this out. Let's say you're mixing up drinks. You're a bartender. And you take 1 shot of 80 proof vodka. You mix it with 3 shots of some kind of juice to make a drink. Hey, what's the alcohol content? What's the alcoholic proof of the resulting drink? Oh, C1V1 equals C2V2. All we're doing here is concentration now. Instead of using molarity, we're using proof, right? So the initial concentration is 80 proof. The initial volume was, hey, we used 1 shot. We mixed it with 3 shots of juice, so 1 shot of this, 3 shots of the juice. What's our final volume? Our final volume there is going to be 4 shots. 3 shots of juice mixed with 1 shot of the vodka. and we can figure out what's the final concentration. So if you solve this thing, I'll do it over here. The final concentration, C2, is going to be the 80 proof, the 1 shot, divided by the 4 shots. C2 is going to be 20 proof. So, we started with 80 proof vodka. We mixed up a big old cocktail, a mixed drink that is, 20 proof. So that's your dilution formula. Down at the bottom here I have a sample showing you that you can work the dilution formula forward, backward. You're not going to see something like this on the final, so we're just going to skip this part. Don't worry about it. You can read through the notes if you like, the annotated notes on the website if you need to see that. Next topic to cover here in solutions, another unit of concentration other than molarity. Chemists, when we're working in a lab, when you're cooking away in a lab, the unit we like, the unit that we love is molarity, that big capital M. We love that unit. It allows us to change liters into moles, vice versa. But in commerce, when you're buying and selling chemicals, quite often they express concentration as mass percent. So mass percent, pretty common unit of concentration, and mass percent is the mass of the solute divided by the mass of the whole thing times 100. Like any percent, it's the part divided by the whole. The solute, that's your active ingredient that's dissolved in the solvent. So how many grams of stuff you have, how many grams the whole solution weighs. Hopefully that weighs more because the solution is the solute and the solvent together. So it's the mass of the solute divided by the mass of the whole thing, the solution, times 100. And again, you see that on labels quite often. Here's a bottle of hydrogen. Let's focus in. Okay, there we go. Hydrogen peroxide solution that you might buy in a drugstore. Useful for dyeing your hair, disinfecting wounds, removing blood stains. It's really good at removing blood stains from fabrics. And if you take some time to read the label, you see that it is listed as 3% hydrogen peroxide. That means if I have 100 grams of this solution, I happen to have 3 grams of hydrogen peroxide. So again, mass percent, pretty common unit that you see. A lot of solutions are labeled with mass percent, even though as chemists, we typically prefer molarity. Things are quite often labeled with the mass percent. Show you how this works. Let's say you have a solution of sugar. 15 grams of sugar is dissolved in 350 milliliters of water. Well, water's got a density of 1 gram per milliliter. So this 350 milliliters of water means there's 350 grams of water. What's the mass percent of the sugar? Well, you know the formula for mass percent there. It's going to be the grams of the sugar divided by the grams of the solution times 100, right? Well, how many grams of sugar? This top number. Top number, oops, here we go. Grams of sugar is 15 grams. Oh yeah, so I got 15.0 grams of sugar. How many grams of the solution? How much does the whole thing weigh? Don't say 350. You might be tempted to say 350, but it's not. The whole thing is the 350 grams of water plus the 15 grams of sugar, so that's going to be 365 grams of solution times 100, and you'd say that sugar solution is 4.11% sugar. So that's the mass percent of the sugar in the solution. The next example real quick shows you, I was talking about Coke, what's the mass percent sugar in Coca-Cola. Let's say you take a 12-ounce bottle of Coke. You find that the Coke weighs 380 grams. You let it evaporate. Let all the water evaporate from it. And you find that you have 39 grams of sugar. What's the mass percent of the sugar in the Coke? Oh, the part divided by the whole times 100. So for this one, you'd get your 39 grams of sugar. The Coke is a solution of sugar and water, traces of some other things. So the Coke weighed 380 grams times 100. What is that stuff? 10.2% sugar. So when you're drinking Coca-Cola, you're drinking a solution that tastes really sweet because 10% of the stuff that's going into your mouth happens to be sugar. So that's mass percent calculations. Very last topic in this sugar is osmosis. Osmosis is pretty simple stuff. It's the flow of a solvent across a semi-permeable membrane. What the heck is that? Whoa. Semi-permeable membrane. What is that? It's something that allows one chemical to flow, but it doesn't allow another chemical to flow. Now, my notes are in black and white. Looks crappy. The picture I'm showing you there, I took right out of the textbook, so in the textbook, the picture is a little bit better. It's, this picture in the textbook. That's your picture for osmosis in full color. So what it's showing you here is a U-shaped glass tube. Semi-permeable membrane is right there. And it's showing you pure water on one side. So right here I have pure water. And on the other side I have a mixture of water molecules and solute particles. That's the stuff dissolved in the water. So if we start with this picture, we've got water. We've got water mixed with stuff. The semi-permeable membrane allows the water to come and go. Water can come and go freely back and forth. But the semi-permeable membrane will block the solute. So if the solute can't flow back and forth, the solute always has to stay on this side. If you start with this situation, you start with the solution, the pure solvent, the two liquid levels are equal. If you let it sit there long enough, you'll end up with your tube looking like this with the the liquid level much higher on the left than on the right. How much higher is this? Oh, it depends on the osmotic pressure. Osmotic pressure is the pressure pushing these water molecules across the semi-permeable membrane, and that's what makes the water level go up. So that's osmotic pressure. The thing to know about osmosis is you always flow from a higher concentration. The stuff that can flow, the stuff that can go across the membrane back and forth, goes from a higher concentration to a lower concentration. So here I've got pure water. On this side I have water mixed with some other gunk. So the concentration of the water over here is lower, so my flow is going to be from the higher concentration of water to the lower concentration of the water, and that will make the level rise. Now, there's a process called reverse osmosis with these semi-permeable membranes. You can force the flow to go the other way. If you put a piston in here and you push down on it and you put enough physical pressure on it, you can force the water to flow this way. That's used to purify water on large scales sometimes. Out in Los Angeles, they're building a $1 billion plant where they're going to take seawater, so you got water mixed with salt. You have semi-permeable membranes that will allow the water to flow but not the salt. And you force it to flow through here, and on one side you have seawater, and when you push it through, you end up with nice pure drinkable water, and on the other side you get some more concentrated salt water. So that's reverse osmosis. Now, medically, the important thing about osmosis and osmotic pressure is cells respond to osmotic pressure. Your cells, your blood cells, this is a picture of normal, everyday blood cells floating around in a solution of plasma. The plasma is these dark areas right here. Those dark areas are a liquid called plasma. Inside your blood cells, there's a certain concentration of salt, sugar, things like that. So inside the blood cells there's a certain concentration of solute. Outside of the blood cell in the plasma, you got that same concentration. That's a good thing. That's referred to as an isotonic solution in biology. So the osmotic pressure of the plasma, the osmotic pressure of the solution inside the cells are equal. There's no tendency for water to flow in or out of the cell. That's an isotonic solution. Now, this picture here represents what's called a hypotonic solution. What's that? Oh, the concentration of solute in the plasma is way less than the concentration of solute inside the cell. So you have a higher concentration of dissolved salts and sugars in the cell. In fact, in this picture, I think this is pure water, so it's a very, very, very hypotonic solution. What's going to happen? Well, you got more stuff inside the cell, more salt and sugar. Oh, water's going to flow into the cell, essentially trying to dilute that stuff out, just like in this picture. The water is going to flow this way. The water wants to flow this way, trying to dilute out those solute particles. So water flows into the cell, and the cells will puff up, and they won't function properly. This is actually used in molecular biology if you want to break blood blood cells open, you just put them in a nice hypotonic solution, they blow up like little balloons, and eventually they pop, they spill their guts. It's a very gentle way to open cells up so that they will spill out their organelles, the mitochondria, the nucleus, the Golgi bodies all spill out. I don't think blood cells, yeah, they don't have a nucleus, but not blood cells. Anyway, here in this picture you see a hypertonic solution. And that's one where you have a real high concentration of salt and sugar. So the surrounding fluid is real concentrated in salt and sugar, higher concentration of salt and sugar than inside the blood cell. What's going to happen? Water is going to leave the blood cell, water is going to flow out of the blood cell into the salty, sugary water, and the blood cells shrink up and they don't function very well. So, whenever you're giving a patient an infusion of something, you know, these IV bags, they have to rig it so that the osmotic pressure here matches the osmotic pressure of the blood. Otherwise, the blood cells tend to either balloon up or shrink up. So, again, osmosis. Flow across a semi-permeable membrane. And the membrane in those blood cells is a semi-permeable membrane. And that concludes chapter 13, guys.